Hello everyone. Today I'm going to explain 4 questions from our calculus assignment. So for first question, I'm going to explain how we can compute the speed and the components of acceleration for a plane making a 90 degrees turn while climbing. Let's start with the position of the plane. The path of the plane is given by vector r of t equal to 10 cosine 10 pi t and 10 sine 10 pi t and 4 plus 0.2 t, where distance are in miles and time t is in hours. The plane flies along this path from t equals 0 to t equals 1 over 20. So question A, find the speed of the plane. To find the speed, we first compute the velocity vector by differentiating each component of the position. Vector r of t equal minus 100 pi sine 10 pi t and 100 pi cosine 10 pi t and 0.2. Then we can take the magnitude of this velocity vector, v of t equal to square root of minus 100 pi sine 10 pi t square plus 100 pi cos 10 pi t square plus 0.2 square. Since sine square plus cosine square equal to 1, this simplifies to v of t equal to square root of 10,000 pi square plus 0.04, which is gonna be square root of 98,696 plus 0.04, nearly equal 314.22 miles per hour. So the plane speed during the maneuver is about 314.22 miles per hour, and this speed is constant over time. So second question, find the tangential and normal acceleration components. Tangential acceleration, at, measures the rate of change of speed. Since our speed is constant, we know that at is 0. That means the plane is not speeding up or slowing down during this maneuver. Now, let's look at the normal acceleration, an. This measures how quickly the direction of the velocity is changing. It's the force that keeps the plane turning. We compute it from the magnitude of the second derivative. So vector r of second derivative of t equal to 100 minus 1000 pi square cos 10 pi t and minus 1000 pi square sine 10 pi t and 0. The magnitude is an equal to 1000 pi square, nearly equal 9,869.6 miles per hour square. In summary, the plane flies at a constant speed, so at equals 0, but because it's turning, it has a large normal acceleration to keep it on its curved path. So now let's move to our second question. So we're giving the curve y equal 1/3 x cubed, where both x and y are in miles. The problem states that the maximum safe speed is inversely proportional to the square root of the curvature at the point. We know the car can travel safely at 30 mph at the point 1/3. We want to find out how fast can a car travel safely at the point 3/2 and 9/8. So solution, first let's compute the derivative of y. First derivative of y equal to x squared, and second derivative of y is 2x. At the point 1 and 1/3, derivative of y equal 1 and second derivative of y equal to 2. The curvature is 2 all over 1 plus 1 1 plus 1 square all over 2 over 1 plus 1 square 3/2 equal to 2 over 2 3/2 equal to 2 to square root 2 equal 1 over square root 2, which nearly equal 0.707. At the point 3/2 and 9 over 8, derivative of y equal 9 over 4, second derivative of y equal 3. The curvature is 3 over 1 plus 9 over 4 square to the 3/2 equal to 3 over 1 plus 81 over 16 to the 3/2 equal 3 over 97 over 16 to the 3/2 equal 3 times 64 all over 97 square root 97, which is 192 over 97 square root 97. So if you use calculator, it's nearly equal 0.201. Since safe speed is inversely proportional to the square root of curvature, v2 over 30 equal to square root k1 over k2. So v2 equal to 30 times square root 0.707 over 0.201 equal to 30 times square root 3.52, which nearly equals 30 times 1.88. It's gonna be 56.4 mph. For the interpretation, if the curvature is large, that means the curve is sharp, so drivers need to slow down for safety. On the other hand, if the curvature is small, the curve is gentle and the car can safely go faster. At the second point, the curvature is smaller, so the car can safely travel faster, around 56.4 mph. Third question, the problem is we're giving the temperature function T of x and y equal to 400e to the minus x squared plus y all over 2, where x is larger than equal 0 and y is larger than equal 0. So question A, compute the gradient vector and interpret it. First, we compute the gradient. T equal dou t over dou x and dou t over dou y. Let u equal to minus x squared plus y all over 2. So if we compute the derivative, dou t over dou x equal to 400 e to the u times dou u over dou x equal 400 e to the u times minus x equal minus 400 x e to the u. Dou t over dou y equal 400 e to the u times dou u over dou y equal 400 e to the u times minus 1/2 equal minus 200 e to the u. Thus, gradient of t equal t of x and y. It's minus x and minus 1/2. This gradient points in the direction where temperature increases most rapidly. In the context of heat flow, heat naturally flows in the direction opposite the gradient toward lower temperatures. For question B, find the unit vector where temperature stays constant at 3 and 5. First, compute u at 3 and 5. U equal to minus 3 squared plus 5 all over 2 equal to 9 plus 5 all over 2, which is minus 7. So t of 3 and 5 equal to 400 times e to the minus 7. Gradient at 3 and 5 is 400 e to the minus 7 with minus 3 and minus 0.5. We want a direction A and B orthogonal to the gradient. So minus 3a minus 0.5b equal to 0. So let's choose a equal 0.5. It's going to be minus 1.5 minus 0.5b equals 0, and then this is going to be b equal to minus 3. So for unit vector, 0.5 and minus 3 over square root 0.25 plus 9, it's going to be 0.5 and minus 3 over 3.004, which is nearly equal 0.164 and minus 0.987. So moving in the direction means no change in temperature at 3 and 5. So we computed the gradient as the direction of the maximum temperature increase. The heat flow is opposite to this. The direction we found keeps temperature constant as the car moves along it. Okay, so our last question. The problem is we are told that the cost at location 1 for producing x1 candle is C1 of x1 equal to 0.02 x square plus 4x plus 500, and at location 2 for producing x2 candles, C2 of x2 equal to 0.05 x square plus 4x plus 275. Each candle sells for $15, so the total profit is P of x1 and x2 equal to 15 times x1 plus 15 times x2 minus C1 of x1 minus C2 of x2. So our question question A, find x1 and x2 that maximize profit. First, expand the profit. P equal to 15x1 plus 15x2 minus 0.02x square plus 4x1 plus 500 equal to 0.05 x square 2 plus 4x2 plus 275. So if we simplify this, P is gonna be minus 0.02 square 1 plus 11x1 minus 0.05 square 2 plus 11x2 minus 775. So next, take the partial derivatives. So dou P over dou x1 is going to be minus 0.04 x1 plus 11. And dou P over dou x2 is going to be minus 0.1 x2 plus 11. So set both to 0 to find crucial point. So minus 0.04 x1 plus 11 equal to 0. And so it's going to be, the critical point is going to be 275. And for x2, minus 0.1 x2 plus 11. So for this critical point, it's going to be 110. So for maximum profit, x1 is 275 units, and for x2, it's going to be 110 units. So for question B, this means to achieve the highest profit, location 1 should produce 275 candles and location 2 should produce 110 candles. This balance takes into account both the cost of producing at each location and the selling profit of the candles.